Hi, everybody. Thanks for joining us on this last day of the science sessions for Chandra Data Science. I want to remind you all that we are having self-organized tutorials that start next week, Monday, August 30th, and run until September 1st. There's more information about those on our website, and there's also a form for you to complete that's available here on the Slack channel, and I sent it to you all via email as well. Be sure to sign up for those if you're interested in attending any of those sessions. Today we have a very nice selection of speakers and talks, and two invited speakers, a contributed talk, and two lightning speakers. I'd like to introduce the first speaker. Our first speaker is Katherine Grant, who is joining us from MIT Kavli Institute and will speak to us about understanding and mitigating the charged particle background in X-ray observatories.
Okay, good morning. Thank you to the committee for inviting me. I hope you can see the right slide now. As Rudy said, I am Katherine Grant from MIT, and I will be speaking about the charged particle background on various X-ray observatories. And like all projects, this is not a one-person show. A number of people are involved in studying the particle background on various observatories. But in particular, this was done in conjunction with the Athena WFI Background Working Group. I've listed a number of names here. Most particularly, I want to highlight Eric Miller, also from MIT, who did a lot of the work I'll be presenting, as well as Garrett Schellenberger and Dan Wilkins. So just a brief outline. I'm going to try and motivate why the background matters, and particularly why it matters now. A brief introduction to the components of the background, various kinds of orbits and particle radiation sources, how we do CCD event detection and background discrimination, and what the current state of the art for background modeling and removing is. So the real question is, can we do better? I'll show some analysis of full frame data from Chandra and XMM, and then discuss a relatively new technique that's been called self-anti-coincidence, and some advances in machine learning and neural network in trying to reduce the particle background. So it probably is obvious to a lot of us why the background might matter, but here's a few reasons. Future observatories, particularly LINX and Athena, have very ambitious science goals. And in particular, they're trying to find the first groups and clusters and mapping cosmic structure with time, which requires deep observations of faint diffuse things. The background adds both statistical and systematic uncertainty to those observations and any results. And even now, observations of low surface brightness sources are currently limited by the systematic uncertainty in the background level. So meeting the goals of these future observatories requires both reducing the background as much as you can, and then improving our knowledge of whatever residual background is left. On the right of the slide here is a figure that I took from one of the Athena white papers. This one in particular is the galaxy cluster Abell 2142, and it's showing an attempt to measure the temperature of the gas in the outskirts of the galaxy cluster, in this case at R200, which is 22 arc minutes from the core. So at this point, the cluster itself is quite faint, and you're fighting against various backgrounds to measure the actual quantities from the cluster. In the spectrum shown here, this is a simulated WFI spectrum. The horizontal black line is the simulated particle background, and you can see at higher energies that particle background is dominating your spectrum. So I did say there were various components of the background. I think the easiest way to divide it up is to look at focus X-rays versus everything else. So focus X-rays are things like the diffuse X-ray background from the hot galactic halo or the local interstellar medium, plus unresolved point sources, which are primarily distant AGN. And below 1 or 2 keV, this X-ray background dominates the background. I'm not going to be discussing that today. There are other people who are studying ways to improve how we deal with it. What I'm interested in is the particle background. So that's galactic cosmic rays, solar protons, and particles in the Earth's radiation belts. This is temporally variable. It depends on what kind of orbit you have, and you mitigate it through various shielding choices when you construct your instrument and in event-list filtering. There's a third component, which is the unfocused cosmic hard-ray X-ray background. So this is very high energy X-rays and gamma rays, high enough that they can penetrate your spacecraft and reach your detector. These are constant in time, but the way you treat them is very similar to how you would treat the particle background through choices in your shielding and event filtering, just like the particle background. So on the right is a background simulation that was done for AXIS by Eric Miller. In blue is the unresolved X-ray background, and in orange is a proposed particle background, but for both a high energy, a high Earth orbit and a low Earth orbit. And you can see for either choice of orbit, the blue line dominates below about 1 keV, and the orange line dominates above that. So orbit obviously matters. You can kind of group orbits into 3 types. There's a low Earth orbit, so things like Suzaku, like Swift or New Star. These orbits have exposure to the trapped radiation, like the South Atlantic anomaly and at high polar latitudes. And that depends on your orbit inclination, how much it matters. You receive geomagnetic shielding of external particle sources like the sun and galactic cosmic rays. And again, that depends on your orbit inclination, how much that matters. So your background varies along the orbit as you go through different areas of geomagnetic shielding. The other sort of opposite end is Earth-Sun L1, L2. So that would be like Rosita, that is at L2 currently, and Athena, which currently is proposed for L1, or a lunar resonance orbit, which are very large, long orbits, like what TESS is doing now and the proposed Arcus spacecraft would be doing. In this case, there's no exposure to Earth's trapped radiation except possibly the low density magnetotail behind the Earth. There's also no geomagnetic shielding, so the quiescent particle background is higher than it would be in low Earth orbit. The middle case is a high Earth orbit, and that's what Chandra and XMM are doing. So they do transit through the Earth's trapped radiation at perigee, but the instruments are generally off, so it doesn't really matter in a discussion about background. During the science observations, the environment should be very similar to that at L1 or L2. We don't have a whole lot of data on that, though, and eRosita is giving us the first data of an X-ray instrument at L2, and that continues to be very interesting, and I suggest everyone tune in to reports from eRosita on what they see for their background. There's one exception of how high Earth orbits are different from L1 and L2, we think, and that's the low energy proton flares, which are a very big deal for XMM, are less of a problem for Chandra, but still exist, and are not particularly well understood. So the primary source of quiescent background in high Earth orbit and at L1 and L2 are galactic cosmic rays, primarily protons, but also electrons and helium ions and various other things. The large plot in the upper left shows a measure of the quiescent background on Chandra on ACES S3 throughout the entire 21-year mission. And you can see there's variability on a number of different scales. The quiescent background is modulated by the heliomagnetic field, so it's associated with solar activity. There's a long 11-year cycle, which is the sun's solar cycle, and you can see the background changes by about 2 times. On the right are sort of zoom-ins on this plot on 2 particular time periods. The top is during solar max, and in this case, there's variations due to individual solar storms where you see the background change by up to 10%. It drops immediately after the particular storm, and then it recovers over weeks or months. The bottom panel is showing a segment of this quiescent background during solar minimum. And in this case, there's no significant solar activity going on, but the background continues to vary by up to 5% over a period of days. So there's a lot of timescales of variation that we have to keep track of. And this adds a systematic error generally into trying to determine the background level in any particular observation. So if you're trying to understand the particle background, you need to also understand how do we detect events on a CCD in the first place. So what I have here is a short movie of some randomly chosen CCD full frame data. So this is for S3 on Chandra. It's a back illuminated CCD, and each of these frames is 3.3 seconds. All of your data comes from frames just like this. Nearly everything you can see in this image is due to the particle background. There are a few calibration X-rays in these images, but they're generally so small that I'm guessing over Zoom, you can't even see them. Telemetry limitations require that we can't take each of these frames and send them to the ground. So you have to make choices of what you think is interesting. So there's onboard processing, and it identifies what it thinks are potential X-ray event candidates, and it telemeters a subset of the most likely to be X-rays to the ground. Event candidates are identified as local maxima above some threshold level. And depending on the instrument and the mode on that instrument, only a few pixels around each candidate event is actually telemetry to the ground. Some candidate events are flagged and removed on board as we've determined they're most likely to be particle events, which further reduces our telemetry. And then on the ground, you do filtering on grade or pattern. And that's your G02346 filter that you usually do going from level 1 to level 2, and that further reduces the background. The remaining unrejected background events cannot be easily distinguished from X-rays. But additional contextual information that you've discarded in your full frame data might be helpful in identifying which of these background events are masquerading as X-rays. And on the left is kind of a visual demonstrating this. The white pixels are pixels that are above the threshold level. The green and red pixels are pixels that are both above the threshold and are a local maximum. The red pixels are events that would be discarded as likely particle background events based on their grade. And there's one green pixel in this image that is actually an acceptable grade and would be part of your event list, even though it is clearly part of a cosmic ray event. And if you could see the entire image, you would know that. But if all you send down is the one event and a few pixels around it, you may not be able to tell that it's background and not an astrophysical X-ray. So this is where we are today. This is the current state of the art. We do standard event selection and grade filtering. There are a few specialized modes, and the ACES very faint mode is an example, which allow for additional filtering and reduction of the background by examining the nearest neighbor pixels around your event. You could do a better statistical treatment of the background, modeling it and not subtracting it. And I have a link here to an example. This is Eric Miller's talk at the IACHEC meeting last fall, where he went through a case study using Suzaku and observations of the supernova remnant N132D. And more recently, particle simulation tools like GANT4 have been used pre-launch. This obviously wasn't possible for Chandra and XMM, but is possible now. And that can inform your instrument design choices to reduce the background. However, background is usually outweighed by other needs, like thermal, outgassing, or radiation shielding. So the choices may not always be optimal for reducing the background. So you ask the question, can we do better? there's been a substantial effort by ESA in support of the Athena X-ray Observatory on understanding and reducing all the background components. And I'm listing a little bit of it here, but there's a lot in the literature already from these kinds of efforts. Particularly, I want to point to Arembus, which is a large study, Athena radiation environment models and X-ray background effects simulators. They have a number of papers associated with this. They did systematic analysis of the in situ X-ray background data, primarily with XMM. They've done characterizations of the particle environment in L1 and L2, looking at the different kinds of particles, on the normalization and the spectra, and on variability. And they've done optimization and validation of simulation tools like GAMP4. In addition to Arembus, there's also background working groups for both the WFI and the XIFU, the two focal plane instruments for Athena. In particular, they've done GAMP4 simulations, which have informed instrument design decisions, have also informed the thinking about flight and ground software. They've done studies of stray light, of cosmic X-ray background modeling, and have proposed a magnetic diverter for Athena, which will prevent soft proton flares. Self-ANSI coincidence was very on in this process proposed as a method to reduce the background on the WFI and to meet the challenging science requirement for the particle background. And that's some of what I'm going to be talking about today. So the US participation in the WFI background working group has had a bunch of directions. We've been searching for phenomenological correlations between the unrejected background and particle tracks in full frame data from Chandra and XMM. We've been working on developing methods to identify unrejected background events using those correlations, and then refining and validating these methods using GAMP4 simulations of galactic cosmic rays and the Athena WFI. We're also trying to better understand the origins of the systematic background errors and come up with strategies to reduce them. In particular, we're trying to determine the magnitude and timescale of galactic cosmic ray spectral variability. And then we want to simulate and analyze the resulting unrejected background variability from that spectral variability. So this is a work in progress. I don't have final answers for a lot of these things, but hopefully you can see that it's interesting at least. So the first step was looking at full frame data from existing X-ray emissions, in particular ACIS and XMM. In both cases, we're looking at specialized data modes that telemeter all the important pixel data. So in ACIS, that's a full frame while stowed, and in XMM, it's small window mode with the filter wheel closed and the mid projection off. So these have no sky X-rays and only background. We do standard event finding, and then we identify particle tracks and with image segmentation. So the question is the unrejected background correlated with the particle tracks? And yes, it is. That's not entirely surprising. And that's because primary galactic cosmic rays can interact with the spacecraft and the detector housing on their way in, produce secondary particles, and those secondary particles also create events on the detector that are related to the primary. So I published in 2018 a correlation between numbers of unrejected events and particle tracks. We also found a strong spatial correlation out to 20 or more pixels from the particle track to the related event. So these results confirm that filtering event data by distance to a particle track, which has been called self-anti-coincidence, could potentially reduce the background. This is the second related study looking at XMM, EPIC PN small window mode data. Ezra Bulbul confirmed a significant spatial correlation between particle tracks and unrejected background events on scales up to 30 pixels. And the ongoing work with the XMM data will use the full potential of the PN small window mode data, adding slew and pointed observations, analyzing the full energy band, and characterizing in detail the spectral and temporal variability. And that's work that is currently being done by Gerrit Schellenberger at SAO. So we want to exploit this correlation using self-anti-coincidence. The detector can serve as its own anti-coincidence veto to further reduce the background. So we want to eliminate unrejected background events within a certain distance around each particle track pixel in a partial veto scheme. And that exclusion distance can be tuned depending on your science goal to optimize your signal to noise. Unfortunately, this removes both background events and real X-rays. So you're reducing your systematic error at the expense of statistical precision. So the effectiveness of SAC requires a large enough detector so that you capture both the primary particle track and any secondaries. And you need a short enough frame time that the primary and secondary events from different particles aren't enormously confused. So the WFI hits a pretty good sweet spot there. It's a very large detector, and the frame time is relatively short. It's 5 milliseconds. It also requires that more information is telemetered than we normally are doing for any of the current CCD instruments. And Athena WFI promises to do that. So we are hopeful that you will be able to do more analysis on the ground. And this is work that's being done currently by Eric Miller. And there's a JADIS paper that was just submitted that describes a lot of it. So we're masking around particle tracks. This is an example from a GANT4 simulation. On the left is a simulated WFI frame, so a 5 millisecond frame time. The purple circle is an unrejected background event. On the left is the original frame, and on the right is the SAC rejection regions, and we're going to slowly increase the exclusion distance around those rejection regions. So this is at 5 pixels. We go 10, 20, 50, 100, 200 pixels, and now we've finally rejected the actual unrejected background in this frame. And then 500 pixels, we're essentially rejecting the entire frame, and you're going into a full anti-coincidence veto, essentially. By employing SAC, you can reduce the background as measured in a number of ways. You can reduce the number of unrejected background events. You can sometimes improve your signal to background ratio and your signal to noise ratio, but it's always accompanied by a loss of signal. What it's essentially doing is turning the irreducible systematic errors into statistical errors, which are reducible if you just increase your exposure time. So, for example, the WFI deep survey is planned to be 1.5 megaseconds. So in that survey, if you assume a source size of 10 arc minutes squared, improvements in the signal to noise ratio of up to 35% are possible. And that might be important for some science cases. As I said, the utility of SAC depends a lot on your science case. But since the filtering is done on the ground and not on orbit, there's no impact to science investigations that don't benefit. So it doesn't hurt observations that are not faint diffuse things. These results, as I said, are further described in Eric Miller's JADIS paper. So stay tuned for that.
3 minutes.
Thank you. Okay, and the last topic I want to bring up is work that's being done by Dan Wilkins at Stanford. He's trying a slightly different approach, and he's using a neural network to try and train the neural network to identify the difference between an astrophysical X-ray and events that have been induced by particles. So he's using GANT4 simulated data for his charge patterns due to particle background. And then each event is assigned a probability of being due to a cosmic ray or due to an astrophysical X-ray. And that's what's shown on the right. The left column is the original simulated frame where there are particle tracks and astrophysical X-rays that he's injected into the frame. The middle column is what the neural network has identified as an X-ray, and the right column is what the neural network has identified as a cosmic ray. So this preliminary work with the prototype algorithm does seem to work. On the left is an example spectrum, a background spectrum, where the gray is the particle background filtered with a standard event filtering and grade filtering. And the orange is the improvement, the lower background that you receive if you use this prototype algorithm, which reduced the background events in this band up to 27%. So this is very early work, but we're hopeful that it actually could do better than this with further effort. So this is my summary, which I've said all before. I'll say it again. The observations of low surface brightness sources are often currently limited by uncertainty due to the background level. The background is variable on many timescales, so you need to better understand that variability to reduce your systematic errors. Background events that otherwise resemble cosmic X-rays can be distinguished by context, and in this case, we're looking at proximity to particle tracks. Self-anticoincidence with a variable exclusion radius offers potential for improvements in some science cases, but it does require additional data to be telemetered about the particle tracks. And a prototype neural network filtering also shows promise in reducing the background. Thank you for listening. And I have listed here some papers if you're interested in for more information. And I'm happy to answer questions.
Thank you, Catherine, for that very excellent talk. I learned quite a bit. If you have questions for Catherine, please add them to the Q&A here or put them in the Slack channel talk discussion thread. Catherine, I was wondering about this neural net that you showed us at the end, especially. If I understand correctly, it'll work on the event level, and so would the other ones work in the event level as well? I guess they would. Is that right? So that every event would be tagged as a background or source. And if that's the case, could you then add extra complexity to the neural net to make it identify like components of astrophysical sources?
Potentially, I think, yes, it does look at an individual event and assign a probability of whether it thinks it's from the particle background or an astrophysical X-ray. So I think it's just a matter of coming up with the right training sets and figuring out the right problem for it to solve. But potentially, yes, I think you could assign probabilities for your event being anything you want.
Mm-hmm. And on that same question, before I go to these two that we have in the Q&A, is there anything interesting in the background that you're identifying and removing from our observations?
Depends what you define as interesting.
Is there anything any science that can be done with the cosmic rates and anything like that?
There probably is some. Unfortunately, the way we're running our detectors is optimized to detect X-rays. So you aren't getting full information about like the particle energy. You're not collecting all the energy. So you can learn something, but not as well as you could from a dedicated detector that was intended to look at particles. And there are some papers that are attempting to do that. In fact, some of the Arembus work is using XMM data to try and learn more about the environment that XMM is in, what kind of particles it's seeing.
Great. So we have a question from Harvey Tannenbaum who asks,
hi, Harvey.
Any comments on what is driving Athena to prefer L1 rather than an L2 orbit?
It is actually the particle background. There has been a push to the particle background requirement for Athena is very low. It's extremely difficult to reach. And right now, simulations make it look like that would be difficult. I think the main reason to move from L2 to L1 is better understood. There's a lot more spacecraft running around in L1 for a much longer period of time. So there's a longer baseline of measurements. And there's a belief that the background at L1 is more stable than it is at L2. That's not entirely understood or that it's not entirely certain how true that is, but there are more uncertainties in L2 than in L1. And in a background-driven environment, that was the push from the background working groups, that they would prefer to be in L1 and L2. And the rest of the spacecraft subsystems didn't really have an issue with doing that. So that's why they're thinking of L1 now.
And the next question is from Herman, who asks, what is the possibility of rejecting the background events during data reduction stage by simply matching the timestamps of self-coincident streaks with that of the background events?
Well, that would be essentially a full veto. So depending on what your frame time is, every frame is going to have multiple cosmic rays and X-rays. For something like ACES, where the frame time is 3 seconds, that essentially means you would reject every single frame. There's both background events and cosmic rays in every frame. For something like Athena with a shorter frame time, you get close to the point where that could become useful, but you'd be throwing away a lot of information. At the furthest extreme, if you have an instrument that it is triggered in that every time you have an event, you read it immediately, then you can do exactly that. And that's what like ROSAT and the other instruments that have a full anti-coincidence do. They see a cosmic ray in their anti-coincidence detector, and then they just ignore anything in their detector that happened at the same time. And that's because they're triggered detectors and they see it immediately. So it's not something that works particularly well for the slower instruments like a CCD.
Fascinating. Thanks, Catherine. That's all the time we have for question and answer on right now. If you have any more, please put them into the Slack and Catherine can respond there as well. Our next speaker, if they can begin sharing their slides, is John ZuHone from the Center for Astrophysics, Harvard and Smithsonian, and is going to talk to us about mocking the universe with pyXSIM and SOXS.
Okay. Thank you to the organizers for accepting this contributed talk, and hope everybody's having a good week. And today I want to talk about some software that myself and some others have written and worked on to produce mock observations from simulations and just general simulated data to make Chandra data that we can compare to real observations, but also data for a number of other X-ray telescopes. Sorry, Rudy, I'm having a little bit of trouble. There we go.
I was going to say, click on the window and it should activate.
Yeah. Okay. So today I'm going to be talking about two packages, SOXS, pyXSIM. They do slightly different things, but they're very related. Those are the URLs for them. They're both open source and Python based. And SOXS is kind of the heart of it. So what SOXS does, basically, it's basically three different components. It's input models for X-ray photons that can come from a number of different sources. And that's a simple 2D models, which I'll talk about in the next slide, coming from SOXS itself, or 3D models from astrophysical simulations coming from pyXSIM, or even just a list of photons that you like create and stick into like a text file or something. And then it can ingest these in various ways, and then it can create a what's called a SIMPUT catalog, which I'll explain in a couple slides. But basically, it's a common file format for storing simulated X-ray events. And then this simulated catalog can then go, SIMPUT catalog can then go into a mock observation, which can be performed by the SOXS instrument simulator, or you can make a SIMPUT catalog, in SOXS using one of the various things on the left, and then you can use it to simulate as input in other simulators. So 60, which is a simulator for Athena and for eROSITA, as well as other missions. SIMX, which is a simulator for a number of missions, or MARCS, which of course is the ray trace for Chandra. And then the outputs of these programs are standard in quotes, because you're never going to get it perfectly the same as real observations, but pretty standard event products that you can analyze with things like Chow and F tools. So SOXS includes some rather, built-in simple spectral and spatial models that you can use to create sources. So on the left, you're seeing a couple of thermal spectra, which are absorbed. So these are APEC models that SOX can do. SOX can also create spectral models by reading them in from outputs from XSpec. It also has built-in power law models, built-in emission and absorption lines that you can put in by hand. And then there are a number of simple spatial models like beta models or or annuli or point sources or things like that that you can use to define a number of simplified models of sources. And essentially the middle point of all of this is the SIMPUT catalog. So SIMPUT stands for simulated input. This is becoming a standard file format for mock X-ray observations. The folks at University of Erlangen, who also developed 60, are the ones that have worked on this a lot. And basically you can have 3 different catalog types where you just have lists of photons, RA, DEC, and energy. Or you can just say, I have a point source at a particular place with this particular spectrum. Or you can have 2D images where you have different spatial regions with different spectra. The image defines like essentially a flux as a function of space, essentially. And as I already mentioned, the SIMPUT catalog enables interoperability with other tools which can read these catalogs and use them to produce X-ray observations. So SOX has its own instrument simulator. It simulates a simplified response of a telescope instrument model. So it's not a full ray trace, not pretending to be. Basically, the minimal steps are is that it reads a SIMPUT file. It uses the ARF to determine which events are actually observed from your SIMPUT catalog. It pixelizes the events based on the instrument model. It applies spatial PSF and dithering, and it creates the spectral channels using the RMF. And then it also adds astrophysical and instrumental backgrounds. And some of the instrumental models that we have include Chandra, Lynx, Prism, Athena, although I will happily admit that the model in 60 for Athena is much better than ours. So it's just there for comparison, basically, among others. SOX also provides a couple of tools for modeling backgrounds. So there is a point source background modeler. You can see an example of that on the left. There's a simulated Lynx image. Point source background where we draw sources from a log n, log s distribution. And then there's a cosmological background where we have a essentially a halo catalog drawn from a cosmological simulation, and then based on scaling relations between various quantities, we assign X-ray emission to these halos. And we're looking to improve these models in the future, but you can already see sort of the availability we have there right now. But of course, we don't just want simplified models like, say, isothermal beta models or point sources or things like that. We have real astrophysical 3-dimensional simulations with things like positions, velocities, thermodynamic states, compositions, varying metallicity across the simulation, varying temperature, etc. And what we want is we actually want to create simulated observations of these objects from different lines of sight in different redshifts, whatever. So what we need is we need to first take the physical quantities and then map them through emission models, which tells us what the spectra is going to be for like a given cell or particle in your simulation. And then of course we have to then pass these through instrumental models, which then gives us events, images, and spectra. So here's an example of like a very old simulation from me. The top are like density, slices through density and temperature of a simulation of a galaxy cluster. And the bottom are images and spectra that you might get out of this particular thing. So the package we use for that is pyXSIM, and it's essentially designed to generate these synthetic X-ray observations from 3D models. So simulation outputs, maybe toy models in 3D. So let's say you just put like a few spherical objects in a NumPy array. That would count as a simulation that you could feed to pyXSIM. It uses the Python package YT as a backend to handle 3D data of grid and particle type, because YT supports reading in data from many, many different types of common simulation codes. It's based on the original Fox approach of Biffy et al. 2012 and 2013, which I will describe right now. So pyXSIM basically assumes you have a 3D emission model of the source from a simulation, or perhaps a 3D grid or collection of particles. So you see a little volume element, delta VI there. That could be a grid cell, or that could be an SPH particle if you prefer Lagrangian simulations. And it has a position, and it has a velocity, and it perhaps has some thermodynamic components like rho, T, and metallicity, or maybe it's a source that emits a power law spectrum, so there would be different parameters there. And the idea is that when you couple the physical model on the grid or on the particles to an emission model, and then assume a very large exposure time and collecting area, and by large, it just means larger than the instrument that you plan on simulating, you use all this information to generate a large number of sample photons in the rest frame of the source. Okay, so that's what these look like Y's, but they're actually gammas in whatever silly font I chose for this, the little orange gammas. And then the second thing pyXSIM does is that, well, the first thing is that you can store that sample, which is still in 3 dimensions, to a file, and then you can use it again and again because it's the most expensive operation. You can use it to then project the source along different directions. And then when you project along a particular direction on the sky, the photons are Doppler, and if it's a cosmological source, cosmologically shifted and absorbed by galactic foregrounds. So you can see that a projection direction not only projects everything to a sky plane, which you're not really showing here, but it picks out the component of the velocity that might Doppler shift the photon. If in this case you have a microcalorimeter, which is sensitive enough to measure that. So the types of inputs, so basically anything YT can read, which is a lot, simulation data sets from Flash, Gadget, Athena, Enzo, Arepo, Gizmo, if you're familiar with a lot of those types of simulation codes. And then it has 3 different emission models built in. It has a thermal model using AtomDB. It has a power law model, and then it has a line emission model. And keep in mind that these allow you to change the characteristics of the spectrum as a function of the position of the characteristics of the simulated object. So what I want to do for the remaining time is just give some examples of some science that has been enabled by pyXSIM and SOXS, as well as some of our packaged friends that I mentioned earlier. So the first one is a couple of studies that involve mocks of Chandra clusters from the illustrious TNG simulations, which were used by Nampaka et al. 2019 to determine cluster masses, to train a neural network to determine cluster masses from X-ray images, from Chandra images. And the same sample was used by Su et al. 2020, and Weizmann gave an excellent talk already in this session, as well as Michelle. Weizmann's simulate neural network was used to determine if the neural network could identify whether or not clusters are cool cores, warm cores, or non-cool cores. So, using mock observations to predict cluster properties. Second example I want to show is simulation of Hitomi velocity measurements in a cluster core. As many of us, not most of us know, Hitomi measured velocities in the Perseus cluster. And what we did in this simulation study was show what velocities that Hitomi was likely measuring in a similar cluster to Perseus, a similar simulated cluster, and whether or not Hitomi was able to distinguish how viscous the intercluster medium of the cluster was. Here is a really nice paper and some ongoing work in various directions by Ben Oppenheimer, where he observed galaxies from the Eagle and TNG simulations. using the Eran model from 60, and then he stacked the galaxy images to basically determine if you could use surface brightness profiles to distinguish between different models. So if you had like the 4-year Eran data, could you distinguish, could you see if, say, the Eagle simulation or the TNG simulation was a better fit for predicting the circumgalactic medium around galaxies? And lest you think it's all extragalactic stuff, which of course is, you know, near and dear to my heart, there was also a really nice paper done by Gaoan Zhang in 2019, where he simulated a mixed morphology supernova remnant. So what you're seeing there on the left is a volume rendering of a 3D supernova remnant with a complex morphology. And these simulations included non-equilibrium ionization. So you not only have varying elemental abundances for individual elements throughout the simulation, but you also have varying ionization states. And thanks to AtomDB, we can actually put that into a spectrum and we can simulate that using SOXS. And so the top right, so using pyXSIM and SOXS, but also 60, which was used in this case to handle the Athena XIFU simulation. See, that's what you're seeing with the hexagon images on the top right. And then you're seeing also simulated CRISM and Lynx spectra from the supernova, where you can see line broadening and you can see radiative recombination features and lots of cool things like that that I'm not an expert on because I don't do supernovae, but it's still really cool. And finally, of course, and this is ultimately the reason SOXS was designed is that SOXS is was the simulator to drive a lot of the science case for Lynx. And these are just some of my favorite images that have been picked from the Lynx final report. So on the top, what you're seeing is you're seeing basically a simulation of a deep field, or it's just but you don't have to go very deep with Lynx, of course, compared to Chandra because of the incredible increase in effective area. The HDXI 100 kilosecond footprint is deeper than the 7 megasecond Chandra deep field. So you can see just a ton of like sources in the cosmic web. You can see distant galaxy groups at Z3. And so the top, of course, is a simulation that was done with SOXS for Lynx. And on the bottom, we're looking at combined pyXSIM and SOXS Lynx observations, where you can actually measure the line broadening in a shock that is being launched by the AGN in a Perseus type cluster. So that's what that line profile you're seeing is there, and it gives you a quite complicated line structure. And then on the bottom right, you're seeing a simulated velocity map of an MA2-like galaxy taken from a galaxy simulation with big super winds. Thank you, Rudy. Driven by supernovae, basically. So there's a lot of cool stuff that you can do with these packages, and you can simulate a lot of cool astrophysics and make predictions for current missions and future ones. So I'll just quickly mention some limitations of pyXSIM. So currently, everything is optically thin. So we don't simulate any sources with optical thickness, absorption, scattering. This could come with a synergy with another package, which is really cool, called Trident, which does things like this. Not necessarily in the X-ray band, though. I'm trying to push on that. Currently don't simulate any sources with explicit time dependence. So that's definitely something that can be done, or work with data sets not in Cartesian coordinates, which is probably a niche, but still something that's definitely doable. So again, these are the URLs for the two packages, and then you can also contribute on GitHub if you find a bug, or if you have an improvement, or if you really want to build in time dependence, or you want to get rid of the optically thin limitation, just let me know. Okay, and that's it. Thanks.
Thank you, John, for sharing that with us. I think that's very helpful tools for everyone. If you have any questions for John, please put them in the Q&A or in the Slack channel so we can address those questions. John, naturally, I'm going to ask you about the limitation about the optically thin case. Do you have a timeline or an estimate of how long that might take or how it
So,
can be incorporated?
right. So the main issue here is that basically it will be driven by a use case.
Mhm.
Obviously, my science area is focused on optically thin things where the radiative transfer problem is point A to point B line, basically, and or geodesic if you want to be technical. But if we had a really good use case, then we could definitely go to work figuring out the best way to do it. So it's essentially the fact that the radiative transfer problem becomes a lot more complicated, obviously.
Right. In planetary nebulae, you have the hot plasma surrounded by a less hot plasma that does appear to be absorbing the X-rays. And so I wouldn't be able to just to put a 2D simulation on the sky of a nebula. I need that extra component. Cool. Okay, we have a couple of questions. We have a comment from Johannes who says, if you need open source Python code for photoelectric absorption, there's a Compton scattering and fluorescence for PyXSIM. There is a package called XRs that he's linked to in the Slack channel if anyone's interested in tackling that.
Okay, yeah, I see that now. That's a really good pointer. Thank you.
And John, we have a question from Vinay who asks, sorry if I missed this in the talk, but how do you handle PSFs? Do you perform ray traces off mirror models or use canned profiles?
Yeah, so in this case, we use canned profiles and or images. So we have PSF images that we use. And like I said, the instrument simulator in SOXS is relatively simple. So in the case of PSFs, you do have a PSF that can vary with off-axis angle and energy, but the way it does that is that you have different image models that you can use, and then basically the photon, you decide which one of those you're going to use for the PSF based on the photon energy and off-axis angle. And this is a really good reason why we've decided to use this standard simplet format, because if this isn't good enough, which it won't be for some science projects, then you can definitely shuttle this off to like a better ray tracer simulator like Mark's, for example. So
thank you, John. That's all the time we have for questions for John right now, but if you have any more, please put them in the Slack channel and I'm sure John will address them there. If our next speaker can begin to share their slides. Our next speaker is Lingsong Ge from the University of Geneva and is going to talk to us about fitting AGN X-ray spectral parameters and reconstructing their parent distributions with Bayesian methods.
Okay, thank you very much. Mm-hmm. So good day, everyone. I'm a PhD student from Geneva University, and I'm very excited today to have this opportunity to briefly present my PhD work about using a Bayesian method to analyze a large number of AGN X-ray spectra with typically low signal-to-noise ratio. And the goal of my work is to study the demographics of AGN properties, for example, the distribution of the hydrogen column density NH and photon index gamma, and also their evolution with redshift and so on. So considering the very short time I have, I'll basically summarize our methods and then quickly present a few results of our pilot study on the XM Cosmos survey. So with larger and larger X-ray surveys providing us with spectra of more and more sources, we need an automatic approach to analyze the data efficiently and also with as little bias as possible. However, this is pretty difficult because first, there are many components of the total emission from AGN. For example, here you can see a sketch of AGN X-ray emissions, where we have the primary power law, the soft excess, the reflection and scattering, and also the galactic emission, the thermal emission. So this makes the spectral parameter space highly degenerate and therefore very difficult to constrain each of them. Besides, there is this obscuring material called torus that strongly affects the direct observation of AGN, so the methods of AGN detection and selection suffers from different biases that we need to take a great care of when we analyze the data. So what we have done is to apply the full model, which includes all the components that I just showed for all the sources, no matter how the data quality is. So there's no need for model selection. And in order to take care of this very complicated model, we use a Bayesian approach with a nested sampling method, which is multi-nest, to derive the PDFs. So we use non-informative priors for parameters of interest like NH and gamma, while informative priors for secondary parameters that are difficult to constrain with low count rate data. And these priors are obtained from literature using much deeper surveys like the Swift survey. So in this surveys, those parameters could be measured. Since we're dealing with low count rate data, we obviously have to model the source and background jointly. And the selection function is included in the likelihood function, since our data detection band is different from the data fitting energy band. And also we extract the spectra, not in the classical way, which is from the event files, but we use the aperture photometry with a consistent energy binning. In this way, the RMF and the RF are standardized so that we are able to tabulate expect models in advance by convolving the theoretical models with the standardized RMF and RF. So in this way, during the fitting, we just need to interpolate between the table grades using pure Python codes. So this makes the method much more efficient, which is very important when analyzing a large number of data.
2 minutes.
So now, yeah, thanks. So now we have the collection of PDFs from the spectral fitting analysis. The next step is to use these PDFs to reconstruct the parent distributions. And to do this, we use a forward modeling approach by modeling the parent distribution with a non-parametric model, which is simply a step function, and then forward fitted to the stacked PDFs. So we're not fitting individual PDFs, which is more like the classic way, because for low signal to noise ratio data, there are intrinsic biases in the PDFs that we have to calibrate. So I guess I don't have time to go into the details, but the idea is that similar to the RMF that maps the relationship between the incident photon energy and the output signals distribution over channels, the distribution metric that we define here maps the certain NH value of a subsample in which the sources share the same NH to the stacked probability distribution over NH of this subsample. So if you're interested, please message me in the Slack channel to have a discussion later. So we have applied this method to XM Cosmos survey for pilot study in which we found 819 sources cross-matched with the Chandra catalog. So here I'm showing the results of the NH distribution on the left and the obscure agent fraction versus the intrinsic asteroid velocity on the right. So basically you can see it matches quite well with the reference and already has some more details here. So now I'm working on the application to the XXL survey, which have much more sources so that we can expect to have a more meaningful result. So yeah, I'll stop here. Thank you very much for your attention.
Thank you very much, Lingsong. If anyone has questions for Lingsong, please put them in the Slack and he can address the questions there. We'd like to move on now to our next speaker. Actually, we're going to have a jump in the schedule. Our next speaker is not present at the moment. So we're going to move to our last speaker of the session, who is David Van Dyke from Imperial College London, and is going to talk to us about coherent multi-stage data analysis in high energy astrophysics.
Okay, I think you can, I don't know what's going on, yeah.
Click on the window and it should make it navigate.
So I can, yeah, perfect, thank you. Thank you for the introduction. Yeah, I'm going to be talking about multi-stage data analysis. So what does that mean? I think you all, I'm a statistician, so you all probably know better than I about the dramatic increases in the quality and quantity of data that's available to astronomers, astrophysicists, and really everybody else in the world these days. But in astrophysics, how it's enabling researchers to explicitly model detailed physical processes, so understanding what's going on in the physics at a particular source or the expansion history of the universe or whatever that might be. What that often involves is combining models and data sources that are analyzed by different groups of researchers. So taking the output of one person or one group's research and using it as the input in a subsequent analysis or several subsequent analyses. And in that context, the different groups of researchers might have access to different data, different models. They might make different assumptions. They might have different expertise. Some of them might have different levels of statistical sophistication, astrophysical sophistication, or they might, actually not be astrophysicists at all that you're using in the one example where you're looking at atomic physics. And so what I want to think about or talk about is how we tie these analyses together in a coherent statistical fashion. How do we properly account for uncertainty when we use constants or constraints or parameter values from a previous analysis and our current analysis? And I'm going to go through this looking at a number of examples that again, I have to say I'm a statistician, so I'm going to look at this from the perspective of a statistician. But all of these are collaborative projects that I've been working on with a number of different astrophysicists and other astronomers over the last several years. Again, so we're going to look at several examples. We'll talk about them when I get to them, I guess. Lots of collaborators, different funding sources for different projects. I'm not obviously going to talk about them all. Some of them are here in the room with me today and maybe can help me out if something goes wrong. But I at least want to acknowledge them quickly here. So the first example involves identifying the properties of a physical source. We're looking at a stellar corona, maybe of our own sun. We're looking at, which obviously a hot plasma. And we want to look at seeing if we can use spectral data to estimate the composition, the temperature, the density of that plasma. And any statistical analysis that's going to try to link our spectral lines, observed spectral lines, or the relative intensities of spectral lines with the composition, temperature, density, physical properties is going to go via some atomic physics. So for example, ion-specific spectra and how those ion-specific spectra vary or are expected to vary as a function of temperature and density. And those are going to be necessary inputs, but they are also the product of a sort of statistical analysis and are themselves subject to uncertainty. So we want to think about how we can account for that uncertainty. So going a little bit more into the details, here's a model up at the top. The expected count of a particular spectral line is going to involve the temperature, density, and path length via this emissivity, which is a function of temperature, of density and temperature. And this is going to be given to us as astrophysicists, is going to be given to us by atomic physicists, and there's going to be uncertainty in that quantity. So the multi-stage analysis in this case is two-stage analysis. The first one is what the atomic physicists do to come up with their estimates of these emissivities. And the second stage is what the solar or astrophysicists, how they use the emissivity to learn about the physical properties of the sun or star. Typical strategy is to use a best fit analysis. So that is to say, take one value of the emissivity and treat it as known. But we're going to try to do something a little bit more sophisticated than that to account for the uncertainty in that stage one analysis. We're going to take a Bayesian perspective because Bayesian methods are particularly well suited for kind of carrying uncertainty forward. So what used to be a constant or what might be a constant in a standard approach to this sort of analysis, we're going to replace that with a prior distribution that has uncertainty. So a prior distribution on, say, the emissivities. So how we're going to do that. So again, that's the spectral model up at the top. And we're going to ask the atomic physicists, and they're able to provide us with not one emissivity, but a collection of emissivities that represent their uncertainty in these physical properties. So you can see here, this is that function. They're going to give it to us in a tabulated form. And instead of having one of them, I have capital M, say 1,000 of them. And here, just to give you an idea what that looks like, is a plot of the emissivities for 7 iron 8 spectral lines, and it's plotting how what the intensity should be like as a function, in this case, of the density. So as the density increases, this particular spectral line becomes more prominent. This one here becomes less prominent. This particular iron 8, is not particularly sensitive to temperature, so it makes things a little bit easier. We can look at just one parameter at a time. And you can see those colored lines. One of them is the default emissivity. If you were just going to use a single emissivity, you would probably be using that one. And then the blue and the green ones are ones that we identify as most likely. And you can see they're not quite the same. They're pretty similar. They're all kind of in the middle of the distribution. That's good news, but they're not quite the same. And therefore, we might end up with a bit different answers for our estimates of the physical properties of the corona. So what is our model going to look like? Here I'm going to be looking at the solar corona. So I'm going to have lots of counts, so I can use a Gaussian model. Y is going to be the count in energy bin, energy bin lambda, and pixel k, and it's going to, the mean is going to be that model I had before, and there's going to be some measure of uncertainty. And then I'm going to combine that with my sample of emissivities instead of a single emissivity that I provided by the atomic physicists. Just a quick note that if you come to the next session, you'll see one of my former PhD students, GGU, who's going to be using similar methods to this in an X-ray analysis of Capella. And she'll be looking a little bit more at the science, where I'm looking at kind of the methodology here. So how are we going to fit this model? I want to think about two different perspectives that we might take. The first, I have it listed second here, but the fully Bayesian posterior distribution, because it's kind of the standard thing you might do, at least if you're a statistician. So that means this distribution I'm calling pi, epsilon is the emissivity, theta is all the other parameters I might be interested in. And I'm going to base inference on this distribution here, which is just a factoring of the posterior distribution of the emissivity and the other parameters given y. And I factored it this way so I can make a comparison with the pragmatic Bayesian approach. And the pragmatic approach is exactly the same, except that it replaces the prior distribution, the posterior distribution of the emissivity here with the prior distribution. So what that means is that what I'm going to say is the uncertainty in the emissivity is not going to be affected by my spectral, by my spectra that I'm using in my current analysis. I'm going to let the atomic physicists tell me about the uncertainty in the emissivity. I'm going to leave it at that. So why might I use one of these or the other? Well, from a statistical point of view, the thing you usually use is the fully Bayesian posterior distribution. If you have some data and it tells you about the emissivity, you ought to use it. So it's pretty simple. Use a fully Bayesian approach. What I call cultural, should we really let our current data influence the emissivity? Well, it's the atomic physicists, not me, who knows about emissivities. They're the ones who have the understanding of the physics and of the atom that are making these emissivities the way they are. Do I really want to second guess them, especially when, well, maybe what if I've made a mistake in my models back here? What if there's some systematic error? I've used error bars are off here, or there's just something amiss with my data. Then those errors will then filtrate into the emissivity estimates as well. And well, that will be especially problematic if I use those emissivity estimates for future analyses. So that maybe I'll be introducing biases that way. So I'm going to leave that at that. Computationally, pragmatic Bayesian methods are pretty simple. If you're thinking about using a kind of Monte Carlo, Markov chain Monte Carlo kind of perspective, you would sample an emissivity from that prior distribution that the atomic physicists gave me, just choose one of the 1,000, and then go forward and do my analysis with fixed emissivity, and then repeat. So I sample an emissivity, and then given that emissivity, I sample the posterior distribution of theta, get a new emissivity, get a new sample of the theta. So that makes it so if I have a standard routine for fitting these models, I just use that kind of put a loop around it and go forward. The fully Bayesian is going to require a little bit more thought, probably not too hard in many cases, but it's going to require a little bit more thought than that. Practical, well, if these two distributions turn out to be quite similar, which is not impossible, it may be that my spectral data isn't really very informative about the emissivity. If that's the case, then I probably should just go ahead and use the thing that's a little bit simpler. So we want to kind of see how these issues kind of play out in these examples. So here's an example, actually not yet another example. This is from calibration. So this is dealing with the uncertainty in the effective area for, say, the Chandra X-ray Observatory. And what I have, this is a simulation study, but because I have the true value, so I'm fitting just a simple little Poisson power law model. True value is the purple dot. The effective area that I have is off by a little bit, but by an amount that seems reasonable according to calibration scientists. And if I do my analysis, I end up with bias, a posterior distribution that doesn't cover the true value. If I then account for the uncertainty in the effective area, by that kind of pragmatic approach, I broaden out the posterior distribution. It now covers the true value. So that's good, but I'm not using this particular spectral data set to learn about the effective area. And I can then, in that regard, I can do better with a fully Bayesian analysis, where it's essentially what we're finding is that the effective areas that led to the values of the parameter off to the lower left and the upper right were inconsistent with the data set. So when you use the data set to update the effective area, those disappear. From my posterior distribution, I end up with a narrower posterior distribution, still a lot wider than the original one, but better than pragmatic Bayes, and it does cover the truth. So it looks like it's probably doing a good job. We always like narrower error bars, but if they don't cover the truth, that doesn't do us very good. So back to the emissivity problem, I'm looking at one of the pixels here, and essentially we see the same thing happening. If we just look at one of the margins for one of the parameters, this is the standard analysis, which uses a fixed emissivity. The pragmatic Bayes widens that out. The fully Bayes picks out one of the emissivity and says that it's the most likely or is highly almost certain to be the right one, and I end up with a narrow posterior distribution that's shifted over. This is just one standard deviation. This is the full posterior distribution. The standard deviations of these things are almost identical. You can see that right comparing the blue and the green down here. So it's kind of a win-win. I shift over, but so I have a better estimate, but without much extra uncertainty being carried forward. So that's kind of very nice. And at the same time, I learned something about the emissivity curves. I ran the analysis with 1,000 different pixels and 1,000 different emissivities, and the size of the dots here is the relative probability of each of these emissivity curves. And you can see that most of the pixels agree that the same emissivity curve is the likely one. That's good news, because emissivities oughtn't vary among pixels, right? Because that's the underlying atomic physics should be the same across the solar corona. So this helps us kind of feel better about using a single emissivity, and that we're actually learning something kind of reasonable and consistent across the image. Okay, so let me now shift over to another example. This is disentangling overlapping sources. So a real standard problem in kind of high energy astrophysics. I have an image here. You can see there's point sources that are nearby. Their point spread functions overlap. So if I want to do an analysis of the spectra of each of the sources that are nearby, I have to first kind of split up the photons between them. How am I going to do that in a reasonable way, and then carry the uncertainty in that splitting of the photons between the sources into my spectral analysis? So in this case, I have, again, a two-stage analysis. The first stage of the analysis is going to be clustering. X and Y are my sky coordinates, kind of X and Y on the plot. And this is going to give me the probability that photon I belongs to source J. So I essentially want to find probabilities for each photon as to their source, what source they originated from. And then, so it's a probabilistic classification. And once I have that probabilistic classification with me, can I use that to fit the specific source models in a way that accounts for that uncertainty? Might the photon energies and arrival times improve classification? So this is thinking about how we go about stage one. I don't want to dwell too much on stage one, but just to say that if you were able to see Antoine Mayer's talk a couple of days ago, he was talking about this stage one analysis and using temporal and spectral data to just improve that improve the classification. So just very quickly, this is kind of a review of what he talked about, but the model that we're using is going to say, model the sky coordinates according to the point spread function, the observed sky coordinates, I should say, according to the point spread function centered at the true value, the location of an individual point source. And then we're going to model the energy or the spectra using a simple data-driven gamma distribution. So not using a scientific spectral model, but a simple kind of data-driven model. And we consider using a single gamma and a mixture of two gammas. And this picture over here is showing you that by using two gammas, we got a good fit. This is again from his talk with a particular data set he was looking at. So we have a mixture model of this sort. We can estimate the number of sources. His talk was talking about adding another piece of data, which is the time of arrival. And when we do that, just briefly, you can see this is the posterior distribution for the same data set from the trapezium. The posterior distribution using just the spatial information, and the posterior distribution using the spatial and spectral information of the number of sources. And you can see by including the energy, we get a narrower distribution. So that's good news. But what I want to talk about is how I'm going to then combine this or use this in the secondary analysis of the spectra. So how are we going to do that? So again, stage one is the clustering. Stage two is the source-specific fit of the spectra. So a naive analysis is just going to could do various things, but one thing it might do is just collect the photons that appear on the image within some distance of each of the source locations, and then just attribute those to that source and use those photons for that spectrum. So that's what we're going to call kind of a baseline naive analysis. The fully Bayesian analysis is going to look at this full posterior distribution. Again, I have the X and Y, the sky coordinates, and the energy. And I want to learn about the source indicator, which photons come from which sources, the spectral parameters of each of the sources, and then any other parameters that might be involved, such as the source locations. And this is the posterior distribution I'm interested in kind of getting a sample from, and I'm just factoring this to kind of represent the two stages here. The first stage is kind of on the right. I'm going to learn about which photon comes from what source, and the parameters are associated with the source other than the spectral parameters. And I'm going to use all the data again, the energy and the sky coordinates. And then once I know the Z, that is to say which photon comes from what source, I'm going to condition on that as well, and then use that, use the photons from source one to learn about the spectral parameters of source one. So that all seems sensible enough. And again, how I would do this is I would sample from this distribution, meaning I would sample an allocation of photons to sources based on those probabilities, and then I would, based on that particular sample allocation, I would separate the photons to the sources and then fit each one separately again by a Monte Carlo sample from a spectral model, and then repeat that to get a Monte Carlo sample of all the parameters. Now, that's all well and good, and this is kind of just saying that again. The one thing I want to notice, though, is that there's an important difference between stage one and stage two, whereby in stage one, I'm using this mixture of two gamma distributions for the spectral distribution, and in stage two, I'm going to use a real science-based power law, thermal model, or whatever it is for my spectral distribution, and those are different things. So ordinarily, when you do a factoring of a distribution like this, there's not different model representations for different factors. It's one distribution, right? So what I say at the bottom, but the spectral models for these two stages are non-congenial. It may not sound like it, but non-congenial in this context is a technical statistical term, because this kind of problem comes up quite often in, say, public use data sets, where one person is putting together the data sets for everyone to use based on census records and all that kind of stuff, and another groups of researchers are then fitting models of their whatever models they might be interested in, which could obviously be very different, to the data sets themselves. You get these non-congenial models, and that's something to think about. In this case, it means what we have is an approximation to the fully Bayesian analysis. So here I've just written that down again, the same thing, the same factorization, and I want to compare that what the pragmatic Bayesian analysis would do is essentially the same thing, except that in the pragmatic Bayesian analysis, I don't use the data in the second analysis, the energies, because I'm doing spectral analysis in the second analysis. I don't use that to update the output from the first analysis, which is the classification of the photon. So there's no, and I don't use energy at stage one. I don't use the energy to classify the photon. So that the pragmatic base is a lot more like what you might expect from if you were just not using energy to do the classification. And then there's no problem with this non-congenial models because there is no spectral model in stage one, right? So the fact that using whatever spectral model you like in stage two is completely fine, but you're not using the spectral data to determine which photon comes from what source, so you're throwing away a bit of information. What does it look like in a kind of an actual analysis? So we want to, again, conduct the two-stage analysis. We want to get a Monte Carlo sample. We do that by clustering, getting a probability for each photon, resampling the data set according to those probabilities to associate photons with sources, and then fitting our model, and then repeating that process with a different classification of photons based on those probabilities. In this case, I'm going to use a science-based model, of course. This is, again, I'm looking at these two sources in the red box here because they're kind of overlapping. The top one is quite a bit brighter than the bottom one, and it's the first row and the image at the bottom, and the faint source is at the bottom. I'm fitting an absorbed single temperature thermal model, 4 or 5 parameters in that model. Here, I'm going to just show you 2 of them just to kind of give you some sense of what's going on. The vertical lines are the estimates and errors based on that naive analysis, right? Just associate photons based on how close they are to each of the locations. And the histograms are the histograms of the fitted values of the spectral parameters. And what you want to notice here is that the statistical errors that ignore the uncertainty in the classification of photons, or based on that naive analysis, at least for some of these parameters, are quite a bit smaller than the kind of systematic errors that come from misclassifying photons. So if you just ignore that, the uncertainty from misclassifying photons, you're actually ignoring a pretty important piece of the uncertainty here. So in other cases, you can see here the uncertainty, the statistical uncertainty is actually probably bigger than the uncertainty to the classification of the photons. Maybe you'd be okay there. But the bottom line is that both of these sources of uncertainty are important, and you should try to take account of both of them if you possibly can.
2 minutes.
2 minutes, perfect. Maybe I'll go for 3, we'll see. Last example, shifting away from X-ray observations to cosmology, just to show you one other kind of thing to think about in this context. Could there be an advantage to the pragmatic approach? So this is an example where I think the pragmatic approach might actually be the way to go. Type 1a supernova used for cosmology, of course, because their absolute magnitudes are very similar. There's a common evolution for a type 1a supernova, so you can use a nice normal distribution for their absolute magnitudes, and that means that variance is quite narrow here. And then because of that, I can fit what a statistician would call a nonlinear regression model with their apparent magnitudes, using something like the lambda CDM cosmological model to learn about cosmological parameters like the total matter in the universe or something like that. And we have a lot of statistical power because the residuals, which are those absolute magnitudes, the residuals have very little variance. So we can fit this model relatively well. But as it turns out, and I don't want to talk about that, I've written papers about it, but that nonlinear fit is, that's kind of one of the stages. It's going to be the second stage. Because we first have to identify which are the type 1a supernovas, and that's becoming a bigger and bigger problem because we end up with great new telescopes like the Rubin Observatory that just give us photometric data, and so the classification into type 1a and non-type 1a becomes important. And if I want to do a fully Bayesian analysis, I need to think about not only the distribution of the type 1a, but the distribution of the non-type 1as. And the distribution of the non-type 1as are not a type, right? That's just everything else. So it's the distribution of their absolute magnitudes. Who knows what that might be, right? It's certainly going to have a lot bigger variance in the type 1as. Normal distribution is probably a pretty silly thing to use in that case. So I didn't have the audacity to write down normal distribution. It just has some distribution. But if I'm going to do a fully Bayesian analysis, I need to specify that distribution, and it's going to be important. So let me just show you how that works. In the fully Bayesian analysis, again, I have the non-type 1a model and the type 1a and the non-type 1a model, and say this is the data here is the apparent magnitude. So this is just a cartoon picture in one dimension. But if I have an apparent magnitude down here, I'm going to say, well, that must be from the red distribution, the non-type 1a. Now, if I have an apparent magnitude here, I'm going to say, well, it's likely to be a type 1a because it's consistent with the blue distribution. And so the relative height of those two distributions is what's going to allow me to update based on the current data set, the absolute magnitudes, which objects are type 1a and non-type 1a. That's all completely reasonable, fine, mathematically sound thing to do. But if it's all based on the relative height of those two densities, and one of these densities is based on great science about how we're lucky that non-type type 1a supernovas have similar apparent absolute magnitudes, and the other one is just an ad hoc distribution I wrote down because I needed to write something down. Well, I probably don't want to use that red distribution to update my probabilities. And that's exactly what the fully Bayesian approach allows me to do, right? To use all of my data for everything, whereas I kind of really don't want to use this part of the data to update those probabilities. It's better for me to stick with the machine learning algorithm probably that I used to originally classify the objects as type 1a or non-type 1a. So no numerical results here. This is work in progress. We've done lots of work on stage 1 and on stage 2 separately, but not trying to put them together. But you can see that my bias is towards the pragmatic approach. So I will stop there again. Thank you all. I'm sure I'm a little over time, but thank all of my co-authors for all these various projects one more time. And because this is going to be recorded, I'll just kind of, flash the citations that somebody looking at the recording can look at more slowly later. So thank you very much.
Thank you, David, for that very interesting talk, a very thorough survey of some really cool methods. Do we have any questions for David? Please add them to the Q&A or to the Slack channel, as we have been doing, and I'm happy to ask those questions to David. I had a thought about the first part where you were showing us bringing in those uncertainties in the emissivities of the lines. Is there also a possibility there to get out emissivities for lines that are poorly constrained from spectra? So reversing the problem using astrophysics.
You should be able to, so I went through this. I know I should have probably only done 2 examples, right? I went through this very quickly. Maybe this isn't what you mean, but you do get, this picture here is telling you which of the emissivity, again, this is the sun, so there's 1,000 different pixels. And so if you look at each kind of column here, it's the posterior distribution of the 1,000 emissivity curves. So this is telling me that this one emissivity curve is by far the most consistent, and it's not the default one, right? It's a different one. And so then we tell the atomic physicists, right, this is the one, and they use certain assumptions that led to that emissivity curve. So hopefully we're also going to help them with their science as well.
Yep, great. We have a question from Johannes Buchner. Says, very nice work. I was wondering if you use HMC, and if not, whether you find it difficult to get the Markov change to converge. Non-congenial sounds much better than inconsistent.
Okay, so there's a bunch of different examples that I went through, and so different cases we use different MC techniques, but we do use, for example, in the one that we're talking about here, we do use Hamiltonian MC via Stan, and a Hamiltonian MC also needs a little tuning from time to time, so it can also, it's kind of the thing of the moment, but actually to making sure it is giving you the right answer sometimes can require a little bit of work as well. But yeah, no, how do you make sure? My strategy is always to use something and then something completely different, and then see if I get the same answer. And if I use 2 different two different independent pieces of code and get the same answer for my Bayesian MCMC, then I usually think I'm getting the right thing. The problem is that if I don't, then I have to try a third one, and then hopefully it matches one of the two, and then I know where to look for the error. So.
Right. We have a question from an anonymous attendee that wants to know if you have a good reference or the best reference on pragmatic Bayes.
Yeah, so I would say probably, sorry, I'm gone too far here. If you look at these papers, where we first did this was with, sorry, I'm losing control here. This Zhu paper and Li paper, it was that we first kind of developed all this stuff in the context of effective areas. And there we'll talk, it's kind of a general introduction to the methods are there.
Great. One last question from Carter Ray. Has the fully Bayesian approach been incorporated into modules such as XSpec or Sherpa, specifically referring to the uncertainties on the emissivities?
No. So yeah, so it's a work in progress. But yeah, so though again, we're using Stan for that, those problems. If you're interested in that, though, that's what Gigi is going to be talking about in the next session, and she might will have something to say about the algorithms themselves. But my understanding is it's standalone software still at the moment.
Mm-hmm. Great. Thanks so much again, David. That's all the time we have for questions in this session, and that's the end of this session. So I'd like to thank all of our speakers again for giving their excellent presentations. And I remind you all to tune in for the next session, which starts at noon or in 30 minutes from now, depending what time zone you are. Thank you, everybody.
Thank you.